Hi, welcome to this episode of Emergent Nature. My name is J. Mark Morris. I go by Mark. In this episode, I'll discuss the error that caused science to go off track into general relativity and quantum mechanics. That may seem like an unusual thing to say, since general relativity and quantum theory are generally considered to be successful, effective theories. However, as we will see, an error circa 1900 threw science off track. There is a parsimonious solution to nature. Particle physics and cosmology are in a crisis that has extended 50 to 150 years, depending on how one assesses progress versus confused narrative. General relativity, quantum mechanics, and the remainder of the quantum theories, as well as the lambda cold dark matter of cosmology, are all models classified as effective theories. These effective theories are good at matching observations and in some cases predicting observations. However, these models express no implementation of nature. With no implementation of nature, we don't truly understand how the universe works. We want to understand the fundamentals from whence nature emerges. What we really need is essentially the architectural blueprint of nature. This includes the absolute frame in time and space, the raw materials, the laws of nature, and the universal constants and parameters. I have found the technical false priors upon which the existing theories of general relativity, quantum mechanics, and the standard model of cosmology are based. Once these false priors are understood, it becomes incredibly clear that many interpretations produced by scientists are incorrect, and that the existing narrative is a complete wasteland. The ultimate goal is to find the grand unified theory of everything, the source code to nature, the basis from which the universe emerges. That's what we would really like to know. Unfortunately, our current theories of general relativity, quantum mechanics and its follow-ons, as well as lambda cold dark matter for cosmology, none of those express an implementation of nature. So if we want to find a grand unified theory of everything, we will have to map to those theories. The present crisis in physics and cosmology suggests to me that perhaps an error was made early on in science, in the foundations preceding general relativity and quantum theory. Therefore, when we develop our grand unified theory of nature, it will be a paradigm change. It will be entirely new, yet we will still have to account for the existing theories. They are effective at matching observations and predicting some observations. So they've got something right, even though they have no implementation, and the narrative that they present is rather mixed up. In the 1800s, scientists were working on classical physics, and that seemed to be going very well, a lot of progress being made. And then in the early 1900s, there was a decision or a consensus that classical physics could not explain nature. And so it was, in a sense, set aside. And these new theories that could explain nature came forth. The new theories of general relativity and quantum mechanics, and then its follow-ons, were all very exciting. They could match observations, but they were confusing, very difficult to understand. They have very complex mathematics that is challenging for the best and brightest academics. And they eventually led to a crisis. There's no reconciliation between the quantum theories and general relativity, and there's many enormous open questions in physics. So as I've said, I think what we need to do here is to trace back and look for an error, and I think I've found it. The error is in discarding or setting aside classical physics based on the false assumptions of Lienard and Wiechert. With a different set of assumptions and a proper understanding of unit potential point charges, their magnitudes and speed limits, I believe there is a solution to nature. That solution is a neoclassical solution to nature. It is based on energetic point charges and a dynamical geometry that leads to assemblies that form particles. Now, easy to say that, but we've got to do a lot of work to map between quantum theory, general relativity, and now classical physics as well. How do we map all of this previous science onto this new era, and vice versa? What does it really mean to map between eras? Well, at the simplest level, we would like our new grand unified theory of nature to be able to reproduce what we found with quantum theories and general relativity. They need to be able to create the same kind of mathematical outcome, maybe with different formulas, but the same kind of mathematical outcome to match observations as those theories. We also need to explain how we got so confused and what led to the crisis in science. Lienard and Wiechert were scientists. Among the areas they each researched were point charges, the paths of point charges, the history of the potential emitted by point charges, and the action on point charges when potential intersects with them. Shown in this figure are 2 point charges, A and B. They move around through space and time on a path. That movement is due to the action upon those point charges from all intersecting potential waves. Let's start by looking at the influence that point charge A has on point charge B at time t. What we see is that at time t prime, point charge A has emitted potential that expands spherically and intersects point charge B at time t. The radius of a spherical potential wave increases at the universal constant field speed, which I have given the @ symbol. The speed of potential is not the same as the speed of light c, although they are related, which will be explained in a future episode. What we see is that there is a delay. It is not that the current position of A impacts B at time t. Rather, it is a historical position on A's path where A emitted potential that now intersects B at time t. The distance between A at time t prime and B at time t is given by the field speed multiplied by the time difference between t prime and t. Action occurs when a potential wave intersects a point charge, and this influences the future path of a point charge. This action is not only a function of the distance between A at time t prime and B at time t, but also the velocity of A at time t prime and the velocity of B at time t. This system evolves as a dynamical geometry. This is true whether it is 2 isolated point charges or all point charges in the universe, even if that is a countably infinite number of point charges. There are some fascinating behaviors in this dynamical geometry. Each point charge is continuously emitting a potential wave that expands spherically. In our example, point charge A emitted a potential wave at time t prime that resulted in action on point charge B at time t. That action influences B's path. Yet B is also continuously emitting potential. So when B's path changes, that will be reflected in the potential wave it emits. This wave then results in action on point charge A when they intersect. This dynamical feedback is continuous between both point charges in our example, and in the universe between all point charges. Overall, this dynamical geometry mirrors Mach's principle, but with charge instead of mass. Point charges continuously emit potential that expands spherically, and intersecting spherical potential waves tell point charges how to move. One more point. In our example, we have shown the relationship between 2 point charges, but it is also possible for self-action to occur, where a point charge responds to potential it emitted on its own past path history. We'll cover this topic in detail in a future episode. Lienard and Wiechert's work, which occurred around the year 1900, was based on what was known in science at the time. And so the assumptions were, in retrospect, rather narrow and limited. Let's go through them. There's 3 areas that can be considered assumptions of Lienard and Wiechert. They are the magnitude of the charge, the speed limit of the charge, and the speed of the potential field emitted by the charge. So Lienard and Wiechert chose the charge magnitude Q to be equal to that of the electron or the proton, essentially the known particles at the time. They also knew about light. They were trying to figure out light around 1900, and they understood that there was a constant speed of light in space, and so they set the speed limit of the point charges at c, the speed of light. And they also gave the potential that's emitted by the point charges the field speed of c, the speed of light. These 3 assumptions were part of the reasoning that led to the conclusion that classical theories could not solve nature. My conjecture is that these 3 assumptions are incorrect. Furthermore, I assert that there is another set of 3 assumptions that leads to a simple, straightforward, neoclassical solution to nature. Now, I haven't filled in the answers here. I've left them as open boxes for you to think about, but you actually now have all the clues you need to solve nature. Spoiler alert, you now have all the clues you need to solve nature. I think it is extremely exciting and satisfying to figure out the architecture of nature. Unlike Lienard and Wiechert, we now have the benefit of 125 years more of science, which we can leverage as a reference. Note, however, that many of the narratives in general relativity, quantum theory, and cosmology are incorrect. So part of your task, if you choose to pause here, is to also determine which science to map and which interpretational narratives to reinterpret according to your emerging architecture. If you would like a few more clues, the remainder of this episode will cover the corrections to Lienard and Wiechert's errors, as well as some implications of those corrections. Future episodes will go into increasing detail about how nature operates. Now let's talk about the magnitude of the unit potential point charges Q plus and Q minus. I already mentioned that Lienard and Wiechert, around the year 1900, believed that the point charges Q minus and Q plus mapped directly to the set of charge values that had been observed to that point, which were -1 and +1, which is shorthand for the -1 would be the charge on the electron, and +1 would be the charge on the proton. So this was one of the root causes of the belief that classical physics could not solve nature. And in fact, it is correct that classical physics could not solve nature. But with the additional insight we're going to reveal here, there is a neoclassical solution. The next particle that was discovered that impacted the set of charge values was the neutron. It was theorized by Ernest Rutherford in 1920. It was discovered by James Chadwick in 1932. And so our set of charge values now gets an additional one. We have a neutral or a zero. So we have -1 for the electron, 0 for the neutron, +1 for the proton. And those are all the charge values science knew about. So as they're, again, trying to figure out nature, they're like, okay, well, if we have point charges, let's just assign those to these values. At this point, they'd already dismissed classical theory, and they're well into the general relativity and formulating quantum mechanics. So they didn't go back, as far as I can tell, and revisit Lienard and Wiechert's work. So they didn't have to account for the neutrals, what I'm saying, in terms of the point charges. Moving forward 3 decades into the 1960s, the set of charge values again changed with the discovery of the quarks. These were theorized by Murray Gell-Mann and George Zweig in 1964. They were discovered at SLAC in 1968. And quarks have fractional charge, or what we would call fractional charge. If we have already given and assigned the values -1 and +1 to the electron and the proton, then the quarks have fractional charge. And the set of values, because of particles and antiparticles, becomes -1, -2/3, -1/3, the neutral at 0, +1/3, +2/3, and +1. So that's a big expansion in the number of charge values. It's also clear to me, or at least I didn't find anywhere that they went back and revisited the work of Lienard and Wiechert and the original choice of -1 and +1 as the point charge mapping. I think that the concept of fractional charge should have been a huge clue for science, because it kind of makes sense to rebase on a charge where multiples of the charge could now be used to create the values. In other words, an assembly architecture. So let's close the loop and look at one particular magnitude for the point charges. And this is if we, instead of use the value 1 and -1 for point charges, what if the magnitude was the charge on an electron divided by 6? And likewise, the charge of the proton divided by 6. I've got absolute value markers here, so we're just looking at the magnitude. Now, if the point charge has a magnitude of 1/6 of the electron or the proton, that implies that standard matter particles would be assemblies, that somehow a group of point charges would form possibly at different times to create an assembly that implements a particle, a standard model particle. And so you might say, well, okay, it's going to have point charges. How many of the negative point charges, let's call that the value m, and how many of the positive point charges, let's call that the number n. And we can say that the particle charge is the net assembly charge of an assembly, which would be m times the negative point charge plus n times the positive point charge. And we just add that all up, and that's going to give us the set of charge values. The fermion assembly architecture that I would like for you to contemplate is one that has a neutral core of 3 of each point charge type, as well as personality charges that decorate the neutral core. So 12 total point charges, 6 in the neutral core, and 6 personality charges. The core is made of 3 nested dipoles at vastly different energy. The core is net neutral. We'll talk about it more in the future, but I've given it the name of the Noether core after Emmy Noether, and you'll see why that name is appropriate in a future lesson. The personality charge layer takes on every combination of 6 charges. So 6 negative charges and 0 positive charges yields a net charge of 6 times E/6, which yields E, the charge on the electron. 4 negative and 2 positive charges yields net minus 1/3 charge. And if we have 3 negative and 3 positive charges, that yields a net neutral personality layer. So what you see on the bottom line here is that the set of assembly charges that emerges from this architecture maps exactly to the charge values in the standard model of particle physics. Earlier I mentioned that the speed of the unit potential emission from a point charge is given by this symbol ampersand. That is a universal constant speed. Now, this is going to become a little confusing for those of you well versed in the current era of science, but the speed of a photon is actually not a constant in space. It's a constant in space-time, but it's not a constant in Euclidean space and time, which are the actual background of the universe. So the speed of a photon, and now the photon is an assembly based on our previous discussion, the speed of a photon, c, approaches the field speed of potential in low apparent energy space-time ether. With that background, let's now turn to discussing point charge speed in an orbiting dipole. If we imagine a density of energetic individual point charges, what is the first order assembly that forms? As you might expect, assembly emergence starts with a pair of point charges. Like point charges repel, so two of the same point charges won't form an assembly. Opposite point charges attract and may begin to orbit one another. We can think of individual point charges as assembly level 0, and the orbiting point charge dipole as assembly level 1. What do these orbits look like? If we imagine an isolated orbiting dipole that is not translating through space and time, then the orbit would be circular. However, if the dipole were translating, meaning the dipole has a group velocity, then the path traced by the point charges might look more like a spiral. In some conditions, the orbital might appear more elliptical after subtracting out any translation. In reality, every point charge is moving along a path influenced by arriving spherical potentials from all other point charges in the universe, as well as itself in some cases. In that sense, the orbital paths include perturbations from those influences. As the velocity of the point charge in the orbiting dipole increases towards field speed, in classical physics we would call that relativistic, and we would use the Lorentz factor in some of our mathematics. And as the velocity continues to increase, eventually it could reach field speed. In classical physics, this would be considered where infinities occur, where the Lorentz factor blows up because the denominator goes to 0, and where we have a singularity, say, in the middle of a black hole. Although scientists generally agree that the singularity is just a mathematical oddity to be explained later, the speed equaling field speed is incredibly important. And the reason is that in neoclassical physics, we see that that is the symmetry breaking point. That's the breaking point between the non-self-action region and what we're going to talk about in a minute, which is the self-action region. So, going field speed is interesting, and exactly how you model it is really interesting. You're just beginning to emit the potential. The potential is at radius 0. The point charge is moving along at the same speed at which it emits that potential. So it's pacing with its own wave, but I don't think there's any self-action right there. Now let's talk about what happens when the speed of the point charge in an orbiting dipole exceeds its own field speed. There's no rule against this. We're not talking about photons that move at the speed of light, c, inside of space-time ether. Photons are assemblies. We're talking about the lowest level here, point charges, moving through Euclidean space and Euclidean time in a relationship with their opposite point charge. And it is possible for their velocity to exceed their own field speed. And this is fascinating because as they exceed their own field speed, they are impacted by the potential they emitted in the past, earlier on their path. So this is a region of self-action. This region is completely missed in classical physics. It is not discovered, it is not understood. And I believe it'll be this region that has a lot to do with explaining how neoclassical physics can take over and become the next era of physics beyond general relativity and beyond quantum mechanics. Returning to our previous graphic, we can now fill in the corrected values for Lienard and Wiechert's faulty assumptions. First, the magnitude of a point charge is 1/6 the charge magnitude of the electron or proton. The speed limit of individual point charges is unlimited. The point charge is not an assembly, it is a fundamental entity, and so far I have seen nothing that would limit its speed individually. However, in an assembly, a point charge may have a speed limit. For example, in an orbiting dipole, there is a maximum point charge speed which corresponds to the maximum curvature of the dipole orbit and also relates to the Planck scale. Note that the maximum curvature of a dipole is a form of asymptotic safety that prevents the radius of a dipole going to zero and creating a singularity. How awesome is that for a mapping? Lastly, we have the field speed of the potential emitted by a point charge. This is differentiated from photon speed because the photon is an assembly. All assemblies leverage field speed and path histories in their operational characteristics. Now that we have corrected Lienard and Wiechert's assumptions, we are free to formulate a new model of nature and the universe. Let's go through one such model at a high level. We are going to start with Euclidean time and 3D space. In this model, we don't know when the universe begins or ends in time. We also don't know if space is finite or infinite, and those limits may be unknowable. Inside Euclidean time and 3D space, we find a large-scale density of point charges carrying a large-scale density of potential and kinetic energies. Energetic point charges operate in a dynamical geometry. Depending on the local conditions, point charges at various energies may react and form emergent assemblies. Each point charge in an assembly has a role in how that assembly operates. Some point charges become parts of core dipoles, generating the strong force. Other point charges may take on the role of the weak personality charge. Even Einstein's spacetime is implemented with point charge assemblies, ones that shield their energy so well that they are extremely lightly interactive. All the particles in the standard model of particle physics are implemented with point charges according to an architectural pattern. As we develop this model, we must leverage, reuse, and reinterpret our existing models of general relativity, quantum theory, and the standard model of cosmology. Scientific observations stand, of course, but even they may be reinterpreted with our new understanding of the photon as an assembly and the point charge implementation of our measuring devices. Thank you for watching this episode of Emergent Nature.